Hello, class. Ready to branch out in your learning? Today, we're diving into the wild world of tree-based methods for classification and regression. Think of it as a journey into a forest where each tree helps us make better decisions. Let's grab our virtual axes and start chopping down the complex stuff. Each chop or split helps us make predictions. For instance, if we want to predict whether you'll need an umbrella tomorrow, we look at conditions like weather patterns, temperature, or whether you live in New York. However, not all trees are created equal. Our simple decision trees are like those cute little saplings in your backyard. They do the job, but sometimes they struggle against the big storms of complex data. That's why we don't just plant one tree. We plant a whole forest. Techniques like bagging, random forests, and boosting are our way of creating a lush forest. By combining the strength of many trees through these advanced methods, we don't just get a sturdier forest, but also dramatically improve our predictions. Imagine each tree votes on whether it's going to rain tomorrow, and the majority vote wins. More trees, better predictions. Now, I leave the stage to Dr. O, who will show you the mechanics of decision trees and random forests. Make sure to leaf through your notes and branch out your questions.
Hello everyone, this is Dr. O. Welcome to Classification and Regression Trees lecture. In this lecture, we will be covering decision trees and random forests. Let's dive in. As in many of the methods discussed on this channel, the objective of decision trees is to predict an outcome using a set of predictors. Decision trees operate by dividing the records into subgroups through splits on these predictors. These splits form logical rules that are clear and easy to comprehend. For instance, if the credit score is below 780 and the income is less than $65,000, then the data falls into class 1. Let's consider an example. Imagine a bank attempting to market personal loans to its customers, which are represented on this chart. And in this data set, the blue points represent customers who previously accepted the loan offer, while the orange points represent those who declined. So we have 10 customers with two predictors: credit score on x-axis and loan amount on the y-axis. Our objective is to establish a set of rules to classify these customers effectively. So one possible approach is to start by segregating the customers based on loan amounts. For instance, we could classify customers with loan amounts greater than 776 as follows into one group, with the remainder forming another group. So I have two groups here, the bottom group and the top group. However, this initial classification does not achieve sufficient homogenization. To refine my classification, now we will implement a vertical segmentation approach, which is this. So by doing this, I have now created three homogeneous segments. This is the first group. So the first group is composed of three data, all of which are orange, non-acceptors. The second group is composed of 5 customers, which are all blue. These are acceptors. And the third group is composed of 2 individuals, which are all non-acceptors. The classification that I made can be visually represented using a decision tree, which is as follows. So first classification divided the data into 2 pieces. So in the first group, there are 3 data, all of which are orange, non-acceptors. And in the second group, there are 7 data at the up group. Now I am going to further divide that data into 2 groups. So 2 orange here and 5 blue here. So this box is a bluish box. It's not exactly blue because 2 of them are non-acceptors and 5 of them are acceptors. That's why it's a pale blue. Now the further classification divided data into accepting group and non-accepting group. So bottom line is this. This first group is here. The second group, which is totally blue, is here. And the third group is here. So the colors of these boxes, they represent different classification. Okay, a little bit of terminology. Nodes that have successors are referred to as internal nodes or decision nodes. Nodes without successors are known as terminal nodes or leaves of the tree. And decisions are based on these terminal nodes. Each node displays the rule first, followed by Gini index. So the rule is loan amount. The rule is loan amount here, and then Gini index, and then shows the sample, and then shows the division. So it's divided by 5 by 5. So based on my data, loan amount is the most important factor in determining the default, and then comes the credit score. However, for those who have a small loan amount, credit score is not important, which are this group. Well, the good part of decision tree analysis is that it provides easily understandable rules, and it does not have any equations or mathematical representation, so it can be understood by anybody who are not expert in math. Okay, let's take a look at this example. First, it says the customer has a loan of $140,000. So let's look at the first rule. The first rule is asking the income, is it less than 102.5 or is it more than 102.5? So the answer to first question is no. So this is always yes, and this is no. So we go to the right branch. So if the income is 140, we are in the right branch. And then comes the loan amount. So if the loan amount is less than 776, we are in the left branch here. If it is higher, we are going to be in the right branch. And the question, the loan amount is given as 780, we are in the right branch here. Answer is no. So the customer is classified as a blue group, which is an acceptor. So as you can see, the last information, which is family size of 2, is not used in this example. So not all the information, all the predictors are used in the decision trees. Okay, the next question is, how are the trees produced? The key methodology behind decision trees is called recursive partitioning, which works basically as follows. First, we pick one of the predictor variables, let's say x1, and then pick a specific value of that x1, that predictor variable, that divides the training data set into two portions. So this will split our data set into two groups. One where the values of x are higher than that boundary value, and one where the values of x are less than or equal to the boundary value. And then we are going to measure how pure each portion based on a metric, which is going to be Gini index in our case. After a maximum purity is achieved, after trying values of x, we will find the one that results in the highest purity. And then we will keep repeating the process for a second split, and after finding the best split for one predictor variable, we will move on to other variables. So I'm going to illustrate this in an example, but before that, let me define what a Gini index is, because we are going to use Gini index for purity measuring. So the formula of Gini index is 1 minus the summation of all squares of proportions of each data group. The lower the Gini index, the higher the purity. So 0 Gini represents maximum purity. We will use it to measure how impure are the data groups, rectangles. Let me show you how to calculate the Gini index for the example we used a moment ago. So Gini index is calculated as follows. We first compute the proportion of each data group in that rectangle, and then we take the squares of all proportions and subtract it from 1. In this data set, we have two types of data, the orange data and the blue data. In total, we have 10 data points, 5 of which belong to orange, 5 of which belong to blue data set. So the proportion of orange data is 5 out of 10. And similarly, the proportion of blue data points is also 5 over 10. So Gini index is going to be 1 minus the summation of these two proportions squared. So this square belongs to blue data point. This square belongs to orange data point. So Gini index is 0.5, which corresponds to the case where all classes are equally represented. A Gini index of 0 represents a perfectly pure node where all elements belong to the single class, making it an ideal target in creating splits. Decision trees aim to minimize the Gini index at each step, leading to the most significant decrease in impurity, which ideally results in a more accurate and generalized model. Let's proceed to first partitioning. Let's assume that we partition the data from 776 as we did before. Okay, as you can see, there are two rectangles here, the upper rectangle and the bottom rectangle. And we are going to calculate the Gini index in both rectangles, for both rectangles. And we are going to take a weighted average at the end. In the first rectangle, there are 3 orange points and 0 blue points. Therefore, the proportion of orange is 3 out of 3, and the proportion of blue is 0 out of 3. So this is the orange proportion, this is the blue proportion. And therefore, Gini index gives 1 minus 1 minus 0 gives 0. So, which is the most purest case. So Gini index of the bottom rectangle is 0. And this illustrates a very extreme case. If a rectangle is composed of pure data, only one type of data, its Gini index is always 0. How about the upper rectangle? So what is the Gini index of the upper rectangle? Well, in the upper rectangle, there are 7 data, out of which 2 are orange and 5 are blue. So if you do this calculation, the Gini index of the upper rectangle is 0.408. So what is the Gini index of the whole split that we performed? Where we are going to calculate a weighted average. So the Gini index of the bottom rectangle is 0 times the proportion of data in that rectangle. There are 3 out of 10 data there. Plus the Gini index of the upper rectangle is 0.408 times its weight. There are 7 data in that data set. So the first split in general gives us a Gini index of 0.286, which is lower than the case where there was no split. Let's remember the case where there was no split. The Gini index here was 0.5. When there is one split, Gini index is 0.286. So we decrease the Gini index by splitting. Therefore, this split is feasible. Now let's proceed one more. Let's proceed a second split. And let's do a second split. The second split divides my data into 3 pieces. So let's say upper left, upper right, and bottom one. So Gini index of the upper left rectangle is 0 just because it is pure. There are only 5 data points and all of which are blue. Gini index of the upper right rectangle is also 0 just because it is also pure. There are only 2 data points and all of which are orange. And Gini index of the bottom rectangle is also 0 just because it's also pure. Therefore, Gini index of the second split as a whole is 0. The weight of first rectangle times it is Gini index. The weight of second rectangle times it is Gini index. The weight of third rectangle times its Gini index gives us 0. Therefore, second split is also feasible. So second split is better than the first split, and first split is better than no split. So that's the idea of building a decision tree. So I made my first split here, and I made my second split here. So that's the idea of basically decision trees and Gini index. Well, another impurity measure is the entropy measure, which is also a linear function of pK with the proportion of records. The concept of information entropy was introduced by Claude Shannon in 1948 and is also referred to as Shannon entropy. I'm not going to cover this idea more. This is just for information. So should we get a tree like this? Well, this is called overfitting. So overfitting is a significant issue in decision trees primarily because it leads to models that are very well tailored to the training data but perform poorly in the unseen data, which is the test data. So one problem decision trees have is that they are very unstable. If 2 or more variables are of roughly equal importance, which one our model chooses for the first split can depend on the initial partition into training and validation. So a different partitioning into training and validation could lead to a different initial split, which can produce a very different tree. So there are 2 solutions to this problem. The first one is called cross-validation, and the second one is called random forest. The idea of cross-validation is you partition the data into sets, which are called folds, fit the model with the training fold, evaluate that model with the holdout fold, and then repeat this for all folds. For example, in the first step, you are going to use the first 4 folds as a training data set. So this part is going to be your training data set, and the last part is going to be your validation. So this is going to be validation. This is the first step. So you evaluate the performance of your model based on this validation. And then you change the validation. So in the second step, this is going to be your validation set. In the third step, this is going to be your validation. And in the fourth step, this is going to be your validation. And in the fifth step, this is going to be your validation set. So you are going to have 5 different validation sets. You evaluate your model based on an average of your 5 different validation sets, instead of using only one validation set. So this is the idea of cross-validation. Now let's come to random forest, which is the second solution to instability problem. The idea of random forest is based on a concept called bagging. The idea of bagging is based on 2 fundamentals. The first one is we are going to create training sets, which is called bootstrap, and we are going to aggregate the results based on these training sets. I'm going to explore this further in an example in a moment. And random forest is just one step further of bagging idea. There are 3 main fundamentals. The first fundamental is draw a random, where the random name comes from, m subsets of p predictors with replacements. For each subsample, we are going to fit a tree, and we are going to aggregate the classification based on these results, which is called the forest. So let me illustrate this in an example. So assume that this is my data set. I have 10 customers with 4 predictors. The first predictor is loan amount, second predictor is the term, and the third predictor is credit score, the last predictor is income. So if this is my data set, I have the right tree as a decision tree. So this is my tree produced by Python. But let me illustrate this instability problem. Assume that I changed the data sets very slightly. So I changed only the income of the 7th and the 8th customer. As you can see, I have a totally different tree. The first split of the first tree was starting from income. Now the first split is based on the loan amount. And the second split here is loan amount again. So as you can see, even the ultimate case is different. In the first decision tree, I have 3 groups of 4, 1, and 5 each. In the second tree, I have again 3 groups, and I have 3 individuals in the first group, 5 individuals in the second group, and 2 individuals in the third group. So this is just to illustrate that the tree idea, the decision trees are very unstable. Just a tiny little slight change might end up with a totally different tree. Okay, now what is random forest? Well, random forest, the idea of random forest is to create training sets or pseudo training sets. So let's take a look at our data set once again. So this is my original data set, which is composed of 10 customers. I am going to pick 10 customers with replacement, which is this data set. Okay, as you can see, the customer 9 is repeated twice, and also the customer 1 is also repeated twice, and 4 also is repeated twice. It might be the case that some of the customers might be repeated 3 times. This is a random picking with replacement. How about the predictors? As you can see, I had 4 predictors initially. I picked only 2. So I'm picking m predictors, m as in Mary, out of p predictors. And m should be roughly equal to square root of p. So square root of 4 is 2. So basically in each step, I take 2 predictors and 10 customers, what customers might be with replacement. This is my first training set. And then I'm going to pick once more. This is my second training set. Again, as you can see, customer 5 is repeated here. Customer 1 is also repeated twice. And customer 6 is also here 2 times. But this time, the predictors is not loan amount and income, it is term and credit score. So again, 2 predictors and random picking with replacement. So this is my second training set. So I'm creating new training sets from my original data set here. So I created 2 training sets. I'm going to create one more. So this is my last training set. As you can see, again, some of the customers are repeated twice, for example, 7, but this time my predictors are loan amount and term. So what is the idea? What am I trying to do? Well, for each random picking, I am going to fit a decision tree. So this was my original decision tree, just don't forget it. This is the decision tree of my first training data set. This is the decision tree of my second training set. And this is the tree of my third training set. Well, basically we are done. So let's say that the question is predict the status of a person with income 106, loan 780, term 0, and credit score 717. Well, we are going to look at each training data set and we are going to aggregate the results. According to our original data set, this person falls into this category. So it is blue. According to our first random pick, this person also goes into the blue category just because the income is higher than 102, so it's also blue here. According to our second random pick, this person goes to the orange category just because the term is less than 0.5, so this says orange. And according to our third random pick, this person goes to blue category again. So blue here, orange here, blue here. So according to our random picks, the majority, 2 out of 3, says this person goes into the blue category. According to our original set, this was also blue. So random forest, which is the majority of random picks, says blue, and they are in line with the original data set, but this might not necessarily be the case all the time. The random forest is basically aggregating the decisions of all random picks. As a summary, random forest aggregates the outcome of multiple decision trees. This is an advantage, but the disadvantage is that this is coming at the cost of losing the clear interpretability provided by single trees diagram, because in single tree we can interpret what the decision of tree is, but in random forest we are aggregating multiple, sometimes tens of hundreds of trees, which might not be easy to interpret. So if you are interested in the theory of random forest and decision trees, you can take a look at the chapter 8 of Introduction to Statistical Learning or chapter 9 of Data Mining for Business Analytics. That's all for this session. I hope you enjoyed the video. Hope to see you in the next videos. Bye.